Somewhere right now, a single AI prompt is being processed. Not on your phone, not in your laptop, but inside a warehouse-sized building, filled with thousands of servers, consuming more electricity than a small town. And it's happening millions of times per minute. Data centers used to be quiet background infrastructure. Now, they are becoming one of the fastest growing sources of electricity demand on Earth. In 2018, data centers used about 1.9% of total US electricity. By 2023, that number jumped to 4.4%, and by 2028, it could reach as high as 12%. So what changed? And why are these buildings suddenly straining entire power grids? Let's break it down. The AI hardware revolution. For years, data centers were built around CPUs, central processing units. These are general-purpose processors, good for web hosting, databases, cloud services. Typical rack density, 5 to 12 kilowatts, manageable. But artificial intelligence changed everything. AI workloads depend on GPUs, graphics processing units, designed for massive parallel computation. Instead of processing one instruction at a time, GPUs execute thousands simultaneously. That parallelism comes at a cost. A standard Google search uses roughly 0.3 watt-hours, a single generative AI query. About 2.9 watt-hours, nearly 10 times more. And training large language models is even more extreme. Training GPT-3 consumed around 1.29 gigawatt-hours, GPT-4 over 50 gigawatt-hours. That's nearly 0.1% of New York City's annual electricity use. AI didn't just increase computing, it fundamentally increased power density. Rack density explosion. Let's zoom in. A modern AI server using NVIDIA H100 GPUs can draw between 3 to 5 kilowatts per chassis. Now multiply that across a rack. Traditional racks handled 10 to 15 kilowatts. AI racks, 60, even 100 kilowatts. Some high-performance computing environments exceed that. That's nearly a tenfold increase in localized power density. And power density equals heat. Every watt consumed becomes heat, which means these facilities aren't just power hungry, they're thermal furnaces. Air cooling, once standard, caps out around 20 to 35 kilowatts per rack. Beyond that, liquid cooling becomes mandatory. Direct-to-chip cooling circulates coolant through cold plates attached directly to GPUs. Immersion cooling submerges entire servers in dielectric fluid. The digital revolution is now a thermal engineering challenge. The grid stability problem. But here's where things get serious. Data centers are not traditional industrial loads. Steel mills and factories use inductive motors. Data centers use power electronics, converters, inverters, switch mode supplies, and these behave differently on the grid. They have low mechanical inertia. They respond in milliseconds. If voltage dips, protection systems can instantly disconnect the facility. This is called the self-preservation paradox. To protect sensitive equipment, data centers drop off the grid, but if dozens disconnect at once, the grid suddenly experiences massive load loss. In July 2024, 60 data centers in Northern Virginia disconnected almost simultaneously. The grid saw a 1500 megawatt surplus. Frequency spiked to 60.053 Hz. That's a dangerous deviation. Grid operators must respond within seconds. Otherwise, cascading outages become possible. Data centers don't just consume electricity, they influence frequency stability. Harmonics and power quality. There's another issue. Harmonics. Power electronic converters generate third, fifth, and seventh harmonics. Total harmonic distortion, or THD, can exceed 5%. In parts of Loudoun County, Virginia, over 6.8% of homes recorded monthly readings above 8% THD. That level can overheat transformers and damage appliances. and AI workloads fluctuate rapidly. Power demand can swing by 10 to 20 megawatts in under a second. In weak distribution networks, that causes voltage flicker of plus or minus 5 to 10%. The grid was not designed for this level of dynamic electronic load. The timeline mismatch. Now add time into the equation. A hyperscale data center can be built in 12 to 24 months. New power plants, 5 years or more. New high-voltage transmission lines, often 5 to 10 years. This mismatch creates bottlenecks. Northern Virginia, sometimes called Data Center Alley, handles roughly 70% of global internet traffic. By 2022, data centers accounted for 21% of Dominion Energy's electricity sales. Peak demand is projected to more than double by 2040. And when extreme weather hits, in January 2026, the US Department of Energy allowed some Virginia data centers to operate solely on diesel backup generators to preserve grid capacity. There are an estimated 10,000 backup generators in Virginia. About 2,000 are large Tier 4 units. During peak operation, emissions can rival small power plants. The infrastructure simply can't expand as fast as digital demand. Cooling versus water, the hidden trade-off. Efficiency is measured using power usage effectiveness, or PUE. It's the ratio of total facility power to power used by IT equipment. The global average PUE, around 1.80. Hyperscalers like Google and Microsoft report PUE values as low as 1.06. Impressive. But achieving that often relies on evaporative cooling. Large data centers can consume up to 5 million gallons of water per day, equivalent to a town of 50,000 people. Water usage effectiveness, WE, becomes the trade-off. Low PUE can mean high water stress. So the energy problem becomes a water problem. The energy independence shift. With grid delays stretching years, tech companies are changing strategy. Behind the meter power. Bring your own power. Microsoft signed a 20-year agreement to restart the 837-megawatt Unit 1 reactor at 3 Mile Island. Google partnered with Kairos Power for small modular reactors, SMRs, targeting 500 megawatts. Amazon is pursuing a 960-megawatt SMR facility in Washington. Hydrogen fuel cells are also entering the picture. Bloom Energy's solid oxide fuel cells can be deployed within a year. Oracle is installing on-site generation within 90 days to bypass interconnection queues. By 2030, these independent systems could meet 1/3 of incremental data center demand. The data center of the future may be as much a power plant as it is a computing facility. So are data centers draining the grid? Yes, in the short term, but they are also forcing the fastest evolution of grid infrastructure in decades. Liquid cooling, waste heat reuse, small modular reactors, hydrogen systems, 24/7 carbon-free matching. The real question isn't whether AI consumes power, it's whether we can redesign energy systems fast enough to support it. Because the future of artificial intelligence now depends on the future of electricity. What surprised you most? The gigawatt scale loads? The harmonic distortion? Or the nuclear comeback? And if you want more deep dives into the engineering shaping our world, subscribe, because the grid story is just getting started.